Okay, so as you may remember, you're doing your counting. This is the second of 4 lectures on Gödel's incompleteness theorems. So today in this second lecture, we're going to get to the main result in some sense, the thing that surprises everyone, or shocks everyone when they first learn about it, which is that it's impossible to axiomatize the notion of truth about natural numbers. So we're going to get that result today. But in a sense, in a not very interesting way, we're going to require a few results from computability theory to get there. And as I've said to people in this class several times, I mean, several of you did the computability theory course last year. It's not important if you didn't do the computability theory course. Just today we will borrow some results from computability theory to get our incompleteness result, that we cannot axiomatize the truths of arithmetic. But if you don't know the computability theory, that doesn't matter, because in the remaining 2 lectures on Gödel's incompleteness theorems afterwards, so after the May holiday, we're then going to revisit the incompleteness, the impossibility of axiomatizing the truths of natural numbers in 2 actually more interesting ways, both of which are due to Gödel, and we will have fully self-contained proofs of the results in those cases. In fact, today's lecture is going to be the only lecture of the 4 lectures on Gödel's incompleteness theorem that does not contain any interesting ideas from Gödel himself. So there might be some, but the other 3 lectures are all substantially due to Gödel's work. This is a bit of a detour in a sense, but it allows us to quickly prove this main result, that we cannot axiomatize arithmetic truth. So let me remind you where we were, or where we are rather, not where we were. So where we are is what we did last week. What did we do? Oh yes. So last week we introduced the language of arithmetic. So we had this signature which had addition and multiplication and this successor function on it. So this is the language of arithmetic. We can use for expressing properties about the natural numbers. And then we considered formulas over this signature. And we identified some simple formulas. There were the delta zero formulas, which only allowed bounded quantifiers. The bounded meant they're given an upper bound, so we can say for all x less than equal to some term, or for all x, or there exists an x less than equals, or strictly less than. The point is that by putting a bound in, you're making the quantifiers finite. In this case, because we're quantifying over the finitely many natural numbers less than a bound. And we have the sigma 1 formulas. So a sigma 1 formula was a formula that starts with possibly with some unbounded quantifiers, existential quantifiers, and then has a formula A inside where this is, where A is delta zero. And our important main result last week was this result that I already forewarned you about at the start of the course, which was that we could rather non-trivially, we can express exponentiation in this language. So the main result was that exponentiation x to the power of y is sigma 1 representable. So the graph of the exponential function, of the exponentiation function, rather, representable, is representable by a sigma 1 formula. Okay, so what we want to do today is address the question of, we know what the formulas are, so the ideal, I mean, we know it's impossible because I've told you it's impossible several times, but Gödel's incompleteness theorems are now part of the folklore of mathematics. So even before starting the course, you probably knew this was going to be impossible. But in an ideal world, what we would like to do is we would like to axiomatize the truths of the natural numbers. So the truth of the natural numbers, well, in our language, that's the theory generated by the structure given by the natural numbers with the usual 0 plus multiplication and successor on it. 0 plus multiplication and successor. So this is an important structure because it's our standard model, if you like, the intended model for this language. So let's give it an abbreviation. So henceforth, well, so it's a standard theory. So henceforth, I'm just going to call this the theory of the natural numbers, and I mean the theory in that particular chapter. So we would like to axiomatize this theory. So what we're going to do is consider the canonical axiomatization, Peano arithmetic of this theory, and then work towards showing that Peano arithmetic is not complete. There are some truths that Peano arithmetic fails to include in its axiomatization, and even worse than that, no other axiomatization will do as a replacement for Peano arithmetic. So today, what we want to look at is we want to consider trying to axiomatize this and see that we can't. So that's called the lecture. So the title for the lecture, we'll call it Axiomatic Theories of Arithmetic. Right. So as you know, I've already used the phrase, I've already used the name, the canonical axiomatization for arithmetic was provided by Giuseppe Peano, and it's called Peano arithmetic. So Peano gave a set of axioms, and they're rather simple and concise, so we can write them down on one board. So let's do that. So Peano arithmetic. Or PA in short. So this is the canonical axiomatization of arithmetic. So it's going to consist of 6 axioms plus the induction principle. And the induction principle is going to be an axiom schema. So that's, as we already saw when we were considering proof systems for logic, an axiom schema is a pattern for infinitely many axioms. For the 6 individual axioms, so we're going to have 6 axioms, A1 to A6. plus 1 axiom schema, which we'll call induction. A1 to A6 simply axiomatize properties of the operations. You've got addition, multiplication, and successor, and how it relates to 0. So axiom 1 says I can incorporate these two dots into an equality here. So axiom 1 says that successor is injective. So if the successor of x equals the successor of y, then x equals y. So our axioms are all actually sentences. So really this is for all x, for all y, or we write it more briefly as for all x, y. But as usual, I'm not going to bother to write down the universal quantifiers on the outside. So all the free variables in the axioms are universally quantified. So successor is an injective function. So these axioms do enjoy the properties that axioms are supposed to have from the days of the ancient Greek, that they hopefully specify self-evident properties of the concept. But the idea is the successor operation is generating the numbers, and in doing so it should be injective. And the second axiom says that whenever we apply to the successor something, we never get back to 0. So we've got a sort of acyclicity here. Yeah. Well, anyway, we'll never get back to 0, which is good. Axioms 3 and 4 essentially give a recursive specification of addition. It's traditional to do the recursive specification in the right-hand argument. So if we add 0 to a number, we of course get x back, and if we add, oops, should be a y here. We add the successor of something to x. That's the same thing as getting back successor of x plus y. Just got space to go down to do all 6 axioms. So A5 and A6 are a similar recursive specification of multiplication. So if we multiply a number by 0, we of course get 0. And if we multiply a number by the successor of another number, then that's the same thing as now x times y plus x. Okay, so those are the 6 individual axioms expressing the properties of the operations, and the induction schema is we're going to have an axiom expressing the property of mathematical induction over the natural numbers. So if a property holds for 0, if the property is stable under the successor operation, so if you can prove that if it holds for a number and it holds for the next number, then the property holds for all numbers. So what's the property? Well, a property is going to be expressed by a formula with a free variable that we're considering as the variable of the property. So we're talking about formula A with free variable x is expressing a property of x. But we might allow the formula to have some other variables too. So for a formula, for every formula, A which has a free variable x, but maybe has some other variables y1 up to, do I use in my notes, to yk, and x. So remember, we write this to say all the free variables of A are amongst these variables. We have the axiom A in, which says that if A holds, well, let's leave a bit more space. So if A holds where naught is substituted for X and for all X, if A holds, then A holds if successor of X is substituted for X, then A holds for all X. So again, this is a formula that contains three variables y1 to yk. So what we actually mean by this is for all y1 through to yk. Okay. Yes, hopefully you can see, but by using substitution here, we're saying if property A, we're thinking of for any values y1 through to yk, the formula A expresses a property of X. If that property holds for 0, and if whenever that property holds for X, it holds for the successor of X, then that property holds for all numbers. Just to say, another way we might write this so some nicer notation would be this, potentially. We have for any formula A X. Good morning. What I mean by this notation is we have a formula A. I'm using square brackets here. I'm using square brackets here rather than round brackets. So we have a formula A with some free variable X identified in it, but it might contain some other free variables. So this means formula A with potentially some y1 through to yk and X, but we're highlighting the variable X. And I do that so that I can write the above formula, rather than using the substitution notation. I'm simply going to put what I substitute into the square brackets. So then we would write this as this formula we've got above, the induction schema for A, we can write as simply A of 0. That means 0 substituted for X, and for all X, A of X implies A successor of X. Then for all X, A of X. Okay, so this is just different notation for the same thing. Okay, so Peano arithmetic is these 6 axioms, plus for every formula A, the instance of induction given by the A induction axiom. So that's right. So we've got infinitely many formulas for induction, one for every time we have a formula A and a free variable X that we highlight in A, then we have an induction formula or an induction axiom for that particular formula. So this is an infinite axiomatization because there are infinitely many axioms in the induction schema. But nonetheless, the axioms have a clear pattern to them. What am I looking for? Okay, so so our axiomatization of PA is infinite. There are infinitely many axioms. In fact, I'm not going to do this because it requires some extra work, but it can be proved that there is no finite axiomatization. If you only consider a finite set of the induction schemas, so a finite subset of induction axioms, or any other finite set of axioms, you cannot fully axiomatize Peano arithmetic. You need infinitely many axioms. But moreover, it can be proved that PA has no finite axiomatization. That's a bit of a shame. We can't write down a complete list of axioms on a sheet of paper, although in a sense we can, because we can easily understand this pattern. So we do have finitely many patterns that give us the axioms. And of course, the technical property that holds is that if we have any sentence in the language of arithmetic, we can check to see if it is one of our axioms, because we can check to see if it's one of these 6 formulas. And we can also check to see if it has this form here of the induction schema, because does any sentence that we're looking at, does it actually have this shape? We can, in computer science terminology, we can parse the sentence we've got, look at its structure, and see whether it can be written in this shape. So given a sentence, we can test whether it's one of our axioms of Peano arithmetic. So our axiomatization in...
Can I just ask?
Yes.
Does PA have no axiomatization or the theory of dimensional numbers?
Aha. So PA. So by PA, I mean the theory axiomatized by these axioms. So here we're axiomatizing it by infinitely many axioms, and it has no finite axiomatization. There's no way of giving a finite set of axioms that gives the same theory. Okay. Also, the theory of natural numbers has no finite axiomatization, but I mean, that's a consequence of what we'll prove today. But anyway, good question. Yeah. So Peano arithmetic has no finite axiomatization. However, the axiomatization we've given it, it's not finite, it's necessarily not finite, but it does have the good property that it's computable. So we can test if a formula is an axiom, if a sentence is an axiom. However, our axiomatization and even if you haven't done computability theory, the idea that this axiomatization is computable is not hard to understand, because it simply means, given a sentence, check to see if it's one of these axioms. Easy in this case, you've just got a finite list. And in this case, you check to see if it's got the structure, if it can be written in this form. I mean, if it looks like this for some formula A. So our axiomatization is computable. So the other thing I want to say about Peano arithmetic before going into more technical details is that so this is something I think I said in the second lecture already. For practical purposes, that's for proving properties about the natural numbers. Conceptually, Peano arithmetic is extremely simple. It's define the properties of addition, successor, and multiplication, and to say that our main well, in fact, our only real method of proving statements about the natural numbers is by the most basic form of mathematical induction about the natural numbers. That's what it's saying. It's very conceptually simple piano arithmetic. The remarkable thing is that practical purposes, it seems this is sufficient to do essentially all of number theory that is known to humankind. So there are some not completely true, but it's true enough. So for practical purposes, Peano arithmetic axioms are sufficient for developing non-trivial number theory. So we can prove statements of number theory can often be expressed as statements, as sentences of Peano arithmetic. For example, it's possible to, so although the Riemann hypothesis is actually a statement about complex numbers and the zeros of some polymorphic function on the complex numbers, there's an equivalent state. There's a statement about prime numbers that's equivalent to it, and that statement about prime numbers can be formulated in the language of arithmetic. That's got really not so much to do with Peano arithmetic, as nobody knows if you can prove it or not. But other non-trivial properties of the natural numbers can be proved in Peano arithmetic. So, for example, the prime number theorem. So I already mentioned this in the second lecture, is provable in PA. The prime number theorem says more or less that the probability of a number n being prime is roughly of the order of log n over n. If I remember it rightly, pretty sure that's right. So this is due to Selberg, approved by Selberg and separately, but not completely separately, Erdogan. And it is believed that nobody's managed to give a fully convincing account of it. It is believed that Fermat's last theorem is provable in PA. That is Andrew Weil's proof. It's not easy to translate it to Peano arithmetic, but the essence of it, it is believed, can be reduced to a proof in Peano arithmetic. But people have not actually sort of done the job there to really do this. But anyway, for practical purposes, the Peano arithmetic axioms are pretty good and sufficient for developing arithmetic. They're very conceptually simple. So it's really an important result that our conceptual axiomatization of the natural numbers is not actually complete for establishing all mathematical truths about the natural numbers. So that's today's main result, as I've said. Okay, so today we're going to show, let's squeeze it into this board here. So today we're going to show that PA does not prove all arithmetic truths. But we're going to prove that this is not just the case for Peano arithmetic, but it holds more generally for any reasonable computably axiomatized theory of arithmetic. Moreover, the same applies to, well, in fact, to any consistent computably axiomatized theory of arithmetic. I'll just say theory here in the language of arithmetic. So to do this, what we're going to do is actually show that any consistent computably axiomatized extension of some simple core theory that's much simpler than Peano arithmetic is necessarily incomplete. So Peano arithmetic will be one such consistent computably axiomatized extension of that core theory. But the idea of identifying the core theory is it allows us to identify just a few simple axioms which we can work with, and it's going to be a finitely axiomatized core theory that are enough to establish the main property that if we have a computably axiomatized such theory that contains those simple axioms, then it is necessarily incomplete. And this core theory is going to be called Q, because that's the historic name for it. Let me stick to writing on this board because I want to keep the axioms for the Peano arithmetic there. So we're going to consider some other axiomatic theories of arithmetic, in particular a very weak theory called Q, in which we have a finitely axiomatized theory and we don't have the induction axiom. And then we're going to show that any computably axiomatized extension of that weak theory, if it's consistent, then it doesn't axiomatize all arithmetic truths. But a weaker theory. So Q is defined to be the theory where, again, we take A1 to A6. We're always going to have A1 to A6. Our axioms that just say that we've got successor and addition and multiplication and they behave as we want, plus another axiom. So this looks like a minus now, the way I've written it, but this is 2. So A1 to A6 plus another axiom, which I'm going to call the Q axiom. So AQ for the axiom of Q. So AQ, the axiom, again, for all x. So any number is either 0 or it's a successor. So for all x, either x equals 0 or there exists a y such that x is the successor of y. Okay, very simple property. We didn't need to have this as an axiom. So it's clear we want to be able to prove this as a property of the natural numbers. It's a totally trivial property. We didn't have it as an axiom for Peano arithmetic. Why not?
Because of the induction scheme.
Because of the induction scheme, because it's a very trivial proof by induction. It's like a proof by induction that in the step case, you don't even need to use the induction hypothesis. It's so trivial. But you do need to have a base case and a step case, but that's all you need. You don't need to actually use the induction hypothesis in the step case. Okay, so Q is the axioms A1 to A6 plus AQ. So and what we can see already is that So by what I said, you can prove the Q axiom by induction. Well, let's put some words in. So we have Q is a subtheory. So by this, I mean the theory of Q, if you like, but I'm just going to, how do I write it in my notes? Yeah, I'll just write it like this. So by this, I really mean the theory of Q. So that all the formulas, all the sentences we can prove from Q are contained in, is contained in the theory of Peano Arithmetic. And let's leave a bit more space. And that's contained in the theory of the natural numbers. So this containment is because using induction, we can prove the Q axiom. That's why this first containment holds. And the second containment is simply because our axioms of Peano Arithmetic are that they are all truths about the natural numbers. Induction is a basic true property about the natural numbers. However, in order to prove the Q axioms, we just need to prove this Q axiom. We can do that by using one instance of the induction axiom. So it's an exercise to prove the Q axiom using induction. If you look at the instance you need to prove, it's a very simple formula A that we use in the induction axiom. So in fact, we can prove the axioms of Q. We don't need to use the whole power of the induction axiom. We don't need to use all infinitely many instances. We only need one, in fact. But there's a family of instances, a well-behaved family, that's sufficient for proving the axioms of Q. And that's if we restrict the axioms, the induction axioms, to delta zero formulas A. So just these formulas involving bounded quantifiers. So I delta zero is A1 to A6 plus the family A induction for A delta zero formula. So remember, the delta zero formulas are the ones involving bounded quantifiers only. So we're giving ourselves sort of some of the power of induction, but only for properties that are expressed in a very restricted way. Now, I mentioned last week the delta zero properties are all, in a sense, checkable in polynomial time, for those of you who know a bit about computational complexity. And it's saying I delta zero is saying, in a sense, we'll give ourselves induction for formulas that we can efficiently check the truth of, or something like that. So actually, there's a bit of a philosophical motivation for I delta zero, that some people don't like to believe too much in sort of the notion of arbitrarily large natural numbers, and even the principle of induction is a bit too metaphysical for them, because it involves unbound formulas that have unbounded quantifications over natural numbers. And for those people called ultra-finitists, I delta zero is a much more comfortable axiom, because it only involves properties with bounded quantifiers that can be efficiently tracked. Anyway, just to mention that, so that's the philosophical side. From the technical point of view, it's just a natural axiomatization, in the sense where we have we're restricting the axioms to a simple class of formulas. And last week we had another class of formulas, as well as I delta zero, as well as the delta zero formulas. We had the sort of more expressive formulas that allowed us to put the unbounded existential quantifiers on front, the sigma 1 formulas. So we can also stick in, there are lots of other things one can stick in the middle here that that's a larger class of formulas to do induction on. So we could also look at the theory we get with induction over sigma 1 formulas. So this is A1 to A6 plus a induction A sigma 1 formula. Okay, so the reasons for looking at Q, I delta 0 and I sigma 1 are, well, if you're an ultra-finitist, then you have a philosophical reason perhaps for looking at I delta 0 or something like it. But for us, the reasons for looking at these three theories are going to be technical. It's going to be useful to somehow look at how much induction we need to prove something. You know, for us, the theory of real interest is this one, Peano arithmetic, because it's the one that has the conceptual axiomatization and is in practice sufficient for proving number theory. And the other theory of interest is, of course, the theory of true statements about the natural numbers. And our main goal today, which I keep on stating, but an important part of it is we're going to prove that this inclusion is strict. So Peano arithmetic does not capture all the truths of the natural numbers. Prove this inclusion is strict. In fact, all these inclusions are strict. In the exercise class tomorrow, you will prove that the first inclusion is strict. There are some nice proofs that the first inclusion is strict. Proving the other two inclusions are strict is less straightforward. I sigma 1 turns out to be finitely axiomatizable. I've not given it a finite axiomatization here, but you can give it a finite axiomatization. And you can prove that Peano arithmetic is not finitely axiomatizable, and that proves that this inclusion is strict. Yeah, well, I delta 0 can only prove the totality of representations of polynomial time computable functions, whereas I sigma 1 can prove the totality of exponentiation. So that separates those two theories. But anyway, these are more advanced facts. For us, the important thing today is going to be proving that this, plus any other attempt at trying to get closer to the theory of natural numbers, is always going to give you a strict inclusion. Right, okay, so it's basically 9 o'clock, so we have a break now and start at 9:15. Right, so we looked at these various axiomatic theories, Peano arithmetic being the one of main conceptual interest, but this weaker subtheory called Q, which is interesting because it's got a very simple finite axiomatization, and it's interesting technically because this axiomatization is well chosen, so it allows us to be able to prove the technical results we want to do. Actually known as Robinson's Q, after the Robinson that first proposed the theory. There were three important Robinsons in logic. Abraham Robinson, who developed non-standard analysis, Raphael Robinson and Julia Robinson. I actually can't remember whether Robinson's Q is Raphael Robinson or Julia Robinson, but anyway, it doesn't really matter. One of the Robinsons proposed this theory Q and realized that it was a nice basis for proving a general result about incompleteness. So now that we've got the theory Q, which I've written sort of conveniently on this board, so we've got the axioms, I can state the general result. And the general result is this. So This is almost what we're going to prove today. So the idea is, if we have any theory in the language of arithmetic which is consistent and computably axiomatized, if T is a consistent, computably axiomatized, extension of Q. Being an extension of Q just means the theory contains all these axioms, so can prove all these axioms, then T is inconsistent. Sorry, not inconsistent. It's consistent, then T is incomplete. So Peano arithmetic is such a theory, therefore Peano arithmetic is incomplete. So remember, T is consistent if false is not a logical consequence of T. Just to say, we could use either symbol here, either this semantic entailment relation or the provability relation. There's less to write with the provability relation, but by soundness and completeness, they're the same. So basically, by this we're saying we've got a computable axiomatization of T. False is not provable from those computable axioms, but by soundness and completeness, that's the same thing as false is not a logical consequence of the axioms of T. Namely, the axioms of T are not consistent. Are consistent. So that's consistent. So T is incomplete, remember. So it is complete. Incomplete is not complete, of course. Complete if for all, if it's complete, if for all A, something which goes A, either A is a consequence of T or not A, the consequence of T. It's kind of a trivial remark by this statement, you did it in an exercise class, but just to comment that actually consistent and complete are kind of dual notions logically, because false not being a consequence of the theory T is the same thing as saying for all sentences A, neither, so it's neither the consequence that, sorry, no, hang on. It is not the case, well, let's just look, it's not the case that both T proves A and T proves not A. For any, in other words, consistent and complete go nicely together because for any sentence A, exactly one of A or not A belongs to the theory. And it's rather a trivial point at this stage. And this is a true result. And it would be a nice thing to prove. But there's a slight nasty technical thing in the proof of this. So I'm going to actually prove a slightly weaker result, which avoids that technical issue, which you may cover in a future exercise class, and is still a result that's of huge interest. In that I'm going to weaken the consistent requirement here. Sorry, strengthen the consistent requirement to something a bit stronger than consistent. So I'm actually going to say, rather than I'm going to prove the incompleteness not of general consistent computably axiomatized extensions of Q, some slightly stronger notion, which is what they call one consistent computably axiomatized extension of Q. So here we need a new notion. The T is one consistent if for any sigma 1 sentence, so remember one of these sentences that involves just some existential quantifications and then just bounded quantifiers on the inside, for any sigma 1 sentence A, if A is provable in T, then A is true in the natural numbers. I'll just write it like this, I mean, in the structure of the natural numbers. Okay, so we can only, so T is one consistent if the only sigma 1 sentences that can be proved are true ones about the natural numbers. So of course, we're only really interested in theories that prove true sentences about the natural numbers. And here we're only looking at sigma 1 sentences. So, you know, we're saying for a certain family of sentences, we want our theory to be correct with respect to the natural numbers. So it doesn't really rule anything of interest out. The point is that just the notion of consistent extension of Q includes some very strange theories that have sentences that are not true in the natural numbers that belong to the theory. You can still be a consistent extension of Q and have some false sigma 1 sentences. Hang on. Oh, anyway, well, this technical definition clearly doesn't rule anything of interest out. Let's leave it at that. Right, before going on, I just want to say something about the generality of this theory. So it obviously, not this theory, this theorem, it obviously applies to Peano arithmetic. But more than that, it applies also, so all we're requiring is that you have a computably axiomatized extension of Q. So we've got some way of getting a handle on the axioms in which for sigma 1 sentences, at least, we can only prove true sentences about the natural numbers. So such computably axiomatized extensions could be given, for example, like Peano arithmetic, by axiomatizing properties in this language directly, using the induction and trying to find even potentially some more powerful principles. But this theorem is very general. It applies also to other means of generating a computably axiomatized extension of Q. For example, one such method would be to take the axioms of set theory, which work in a language that's different from the language of arithmetic, but in a language that we can express, that we can define the real numbers, we can express all the properties of analysis, we can derive all the theorems of analysis, and then consider from our axioms of set theory which sentences we can prove, which sentences in the language of arithmetic we can prove about natural numbers, and we take those sentences as our axiomatization of the theory T. Now, by the way we're defining this, those sentences would be a computably enumerable axiomatization, because it's theorems in set theory, a computably enumerable axiomatization in our language of the natural numbers. In the end, we get a set of sentences in the natural language about natural numbers, the language of arithmetic, which is axioms, or which is the axioms we're considering. It's clear that that's computably enumerable because it's those theorems we can prove in set theory. And because we have a computably enumerable axiomatization by a result from a few lectures ago, we therefore have a computable axiomatization. So the point is, I mean, I could spend a lot more time expanding on this in detail, but I don't want to go in that direction. But this theorem also applies to, as formulated here, also applies to as a consequence of this theorem, we get that the truths about natural numbers in a language such as set, in a theory such as set theory, that includes all the analytic tools that we might use for proving using methods of analysis properties of the natural numbers. That theory is also, theories obtained in that way are also incomplete. So this is a very, very powerful, it's a very, very powerful theory. Okay, good. Right, so we want to prove this theorem. So to do so, we're going to have to develop some, in the end, it's a negative result, in a sense, we get an incomplete theory. But in order to prove the negative result, we need to prove some positive results about the theory Q, showing that Q has enough power to at least do something of interest, which is going to provide the basis for the proof of this theorem. So the next part of the lecture is going to be about developing positive results in Q. Right, so and to prove the theorem, we're going to need to prove a positive result about Q, and the main one is this. Positive result about Q. This is a proposition. So if A is a sigma-1 sentence, then if A is true in the natural numbers, that implies that A is provable in the theory Q. Let me underline sentence here. It's really important that we're talking about sentences. Okay, so sigma-1 sentence is a formula A stating properties about the natural numbers that is some existential quantifications. So exists x1 through to xn, followed by a formula that involves possibly universal and existential quantifications, but all of them bounded. So we're saying there exists some numbers such that some property that we can check by finitely many computations because all the quantifiers are bounded is, so the property A says there exists some numbers such that some checkable property that involves only finitely many checks holds. So for such simple properties, it's amazing, but well, it looks quite astonishing. We can always prove them using these axioms of Q that we don't have any induction axioms. So we never need induction to establish such properties. And the intuitive reason for this is because if such a property is true, then there actually exists some numbers for which, there exists some numbers instantiating the unbounded existential quantifiers. And if we instantiate the variables with the numerals for those numbers, well, then we've just got a formula with some bounded quantifiers in. And that formula with bounded quantifiers essentially reduces to a finite number of instances. And a finite number of instances is just a large disjunction. So that's essentially how this works. And notice this property here that in the proposition is establishing the opposite property to the one we the converse property to the property we've used in formulating one consistency. So the theory Q proves all true sigma-1 properties, and one consistency is a natural converse to that. We're saying we're interested in extensions of the theory Q. Any of those proves all true sigma-1 properties, I mean, we're only going to look at those extensions that only prove true, that prove no false sigma 1 properties. Okay, and we want to prove this proposition. So this is called, but there's a word for this. This says that Q is sigma 1 complete. It's true is complete for sigma 1 properties. Okay, so in order to prove it, we're going to somehow build up from basic, we're going to start proving very basic facts about numbers using Q, and then eventually work our way up to sigma 1 sentences. So some example of a very basic property would be something like, can we do computations with natural numbers in Q? So notice that if we consider something like S of S, so this is going to be very simple. This is 3, and we can express 3 using a numeral. So this is 3 plus 2 by A4. We get that this is equal to the successor of by A4 again. This is, we get to another successor coming out of the inside addition, so we get to the successor of S of S of S of 0. Two brackets on the outside, and by A3, x plus anything plus 0 is the thing. So by A3, this is the successor of successor of 0. So that. Thank you. So here I'm just reasoning using equality that this will be true in any model of these axioms, that we can just reason with these equalities and establish that this equality, that this term is equal to this term. And generalizing from this one example, you can see that essentially whenever you plug in numerals for x and y, you're always going to be able to compute out a sum, and by a similar argument, compute out a multiplication. So it's going to be very tedious. It was tedious enough for 3 plus 2, but we get a little lemma. For any numbers, m and n in the real world, we can prove in Q that if we take, I don't remember, did I put the bar on top or on the bottom last week? I remember wondering what to do. Well, anyway, it doesn't matter. This is the numeral for m. We consider the term which is formed from the plus function symbol with the numeral for m on one side and the numeral for n on the other. Then we can prove the equality that this is the numeral for m plus n. This is equal to that. And likewise, if we consider the term m times n, we can prove that this is equal to. Okay. So notice what we're saying here is for any numbers in the real world, we consider a formula generated by those two numbers, and that, in fact, a sentence, and that sentence is provable in the theory Q, and so is this other sentence. And to prove this, we would prove this, well, the first one, well, in fact, both of them, we would prove by induction on N, right? And we can do that because we're talking about proving this for numbers in the real world. We use induction in the real world to prove this property. So it doesn't matter, we don't have induction in Q, we're using induction in the real world to prove this lemma. Okay. Right, so having done that, so let's call this lemma A. So I don't want to erase the axioms for Q. So another way of looking at it is, in a sense, this is again a schematic statement. It's for all of these infinitely many sentences, the sentence is provable. Okay, so lemma B is the main lemma that we need in order to prove sigma 1 completeness. And this is, as I said before, the intuition for the sigma 1 completeness is when we're looking at proving a formula involving a sentence involving only bounded quantifiers, we can reduce every bounded quantifier to a finite disjunction or a finite conjunction in the case of a universal quantifier. And the reason for this is that the following is provable in Q, and it's not. It requires a little bit of work to prove it. So once again, this is a schematic property, which is for all numbers in the real world. A certain sentence is provable that we generate from N is provable in Q. So what's provable in Q is the sentence. Well, I'll put the quantifier in a moment. But I've got this in. I've got this in brackets here. So x is less than or equal to the numeral for N. If and only if, so x is 0, or x is 1, or x is n. Okay, so notice here I need a definition by recursion on the numbers n, even to define this. As I said, this is a sentence, so once again, this is the sentence with for all x here. But again, we can, I mean, this sentence is provable. But once again, I'll avoid writing quantifiers when I don't need to. Okay, so for any number in the real world, we generate the appropriate sentence, and that sentence is provable in Q. So again, we're talking about numbers in the real world, so we can prove this by induction on N. But actually, there are two implications. So maybe we'll prove one implication. The right to left implication is the right to left implication actually doesn't need to be proved by induction. So let's do that one first. So prove. So the right to left implication. So we want to show, so given N, we want to show that this disjunction implies x is less than or equal to N is provable in Q. So this disjunction, so to prove, so we want to show that the theory of Q, this disjunction implies this. So to show that a disjunction implies something, you need to show that every one of the disjuncts individually implies the thing you're trying to show as a consequence. So we need to show that x equals 0 implies that x is less than or equal to n, x equals 1 implies x is less than or equal to n, and so on. So in other words, given n and some n less than or equal to n in the real world, we need that in the Q proves that if x equals n, that's the relevant one of these disjuncts, then x is less than or equal to so in other words, if we want to show x equals n implies x is less than or equal to n, i.e. we must show that Q proves that n is less than or equal to n. The numeral for n is less than or equal to n. But now we remember the definition of the less than or equals. So this is kind of backwards reasoning. I'm just expanding what we're trying to show. I'm expanding what we are trying to show every time. So we need to show this inequality. So that is, we need to show that. So less than equals was defined by there exists a z such that n equals m plus z. But this is easy because by lemma A, we have that Q proves that n is m plus n minus m. Right, so if we plug in the numerals for n minus m here, then by lemma A, this term is equal to n plus n minus m is equal to the numeral for n. So Q proves this equality, and so therefore it proves, because it holds for a particular term, it proves that there exists a z. In other words, m is indeed less than or equal to n. Okay, so that's the right to left implication. I don't know what's happening today. My pick-me-up drink seems to be having less effect than usual. I'm worried about it, actually. Maybe need to move to something stronger.
Tolerance.
Sorry?
Tolerance.
Yeah, well, it's not that I have it so often. Maybe it's kind of body anticipating holiday next week or something like that. Right, so let's do the right to left implication. Sorry, left to right implication. And this is the one we proved by induction on n. So we want to prove this, that if x is less than or equal to the numeral for n, then this disjunction holds. So if and again, this is induction in the real world because n is a number in the real world. And for any number n, we prove this particular formula is provable in Q, a particular sentence, and by induction on n, but not on the numeral for n, but on the number n. So it's the case n equals 0. So we need to show in this case that Q proves for all x, if x is less than or equal to numeral for 0, then this disjunction holds. In other words, x equals 0. Right, so x is less than or equal to 0, so i.e. we need to. I wish I had a better way of writing these proofs, but it seems most natural to do it by sort of backwards reasoning. We need to show this, and in order to show that, we need to show this, and so on. But it seems to be the best way is then to say that is we need to show that sort of, you know, it's the opposite way around to the usual chain of reasoning in a mathematical proof. Anyway, so we need to show, let's expand the less than equals, so we need to prove that if there exists a y such that 0 equals x, so x is less than or equal to 0, so 0 equals x plus y, and that implies x equals 0. Let me just check my notes to see that I'm doing that on auto. Okay, actually, I've written it in a nicer way in my notes. So let's do it. So rather than doing this backward reasoning, we've got the gold here. Let's put that in blue. So we have, so I'm going to work forwards. So from the definition of less than equals, we have that x is less than or equal to 0 is the same thing as there exists a y. 0 is x plus y. Or we can put that the other way around. So x plus y equals. So the numeral for 0 is just 0. So x plus y equals 0. So, applying our axiom for Q, which is this is the reason that we needed this axiom, when there exists a y, well, such a y will itself be, you know, this is for all x, so it can apply to y. So such a y is going to be 0, or there's going to exist a z such that y is the successor of z. So if x is less than or equal to 0, we have this, and this, by the axiom of Q, implies that there exists, so either x plus 0 equals 0, or there exists a z such that y is the successor of z, and x plus y equals 0. Or in fact, we can simplify that to x plus the successor of z equals 0. So this is by axiom of Q. So in other words, Q proves that if x is less than or equal to 0, then well, x plus 0 equals 0, so x plus 0 is x by axiom whatever 3, and x plus the successor of z
is the successor of x plus z, so all there exists is z such that the successor of x plus z equals 0. So this was by, so this is by A3 and A4. But there is nothing whose successor is 0. So this is false. So in other words, Q proves x is less than or equal to 0 implies x equals 0 by now A2, because here we've got the successor of something equals 0. And this is A2. And that's what we wanted to show, because 0 is the numeral for 0. Okay. These proofs are kind of rather simple pushing, but there's always this rather awkward aspect to when one's reasoning in these weak axiomatizations, basically you have to be careful because you're reasoning about natural numbers, which is something you can do with your eyes closed most of the time, but we have to be careful that we're using only the axioms we've got. So I'm writing things out rather in a rather long-winded way, perhaps, but I'm trying to make sure that it's clear that we are really using the axioms we've got. So we've done the base case of our induction step. So it remains to prove the step case. The step case, we want to prove the result for n plus 1. Right. Proving the result for n plus 1, assuming the result for n. So let's write the induction hypothesis down. That's the result we already have available. So I should move the board, not the board, the camera. Of course, it's all relative. Yeah. So the n plus 1 case, yikes. So, right, the induction hypothesis. The induction hypothesis is this left to right implication here, just as written there. So the induction hypothesis is that Q proves for all x is less than or equal to n, then x is 0 or x is 1 all the way up to x is n. And we need to show that we're required to prove RTP, required to prove that for all x is less than or equal to n plus 1 implies x equals 0 or x equals n or x equals n plus 1. Right, so we're going to do, again, I'm going to do this. Right, so this is what we want to show, so let's put it again in a blue box. And again, I'm going to do it by broad style of reasoning. Right, so we have that in Q, we have that if x is less than or equal to n plus 1, and that's the same thing as there exists a y, x plus y equals n plus 1. Again, this is the definition in my explanations in blue, so let's keep it. This is the definition of less than equals. Perhaps set that here. So this was the definition of less than equals. It's that. So once again, we apply the Q axiom here, so that if there exists such a Y, it's either 0 or it's the successor of some Z. So by the Q axiom, we have that x is less than equal to n plus 1 implies there exists a Z such that either x plus so exists a Y such that x plus Y equals that. So either that Y is 0, so it implies that either x plus 0 equals n plus 1, or there exists a Z such that x plus s of z equals n plus 1. So this is the Q axiom. Find the Q axiom. And we just do the same thing as before. So x plus 0 is x by axiom 3. So either x is n plus 1, or, well, we've got x plus the successor of something, so that's the successor of x plus z. So or there exists a z such that the successor of x plus z is the numeral for n plus 1, but that's the successor of the numeral for n. Okay. So that's axioms A3 and A4. But now we've got axiom 1 that says that the successor is injective. So if the successor of x plus z is the successor of the numeral of n, then x plus z is the numeral for n. So we have x is less than equal to n plus 1 implies x equals n plus 1, or there exists a z such that x plus z equals n. So this is now A2. But this simply says, this is the formula saying that x is less than or equal to n. So this says x is less than or equal to n. And hence, by the induction hypothesis up here, here's the induction hypothesis, x is less than or equal to n implies x equals 0, or one of the, it implies this whole disjunction. And now by the induction hypothesis, we can replace this with the whole disjunction x equals 0 or x equals 1 all the way up to x equals n. So we get that Q proves that x is less than or equal to n plus 1 implies either x equals n, the numeral for n plus 1, or this disjunction from the induction hypothesis, or x is equal to 0, or so on, or all the way up to x equals n. So this is by the induction hypothesis. And this is the disjunction modulo. They're not quite in the same order, but of course that's the same thing as what we wanted to prove. Yeah. So we're done. Okay, so that's the kind of reasoning that one does. And to prove very simple things in Q, but and what we've got now is we've got our lemma that allows us to say that being less than the numeral is equal to this disjunction. And it's already 10 o'clock, so we'll have a break and start again at 15:15. So we were on our journey, if you like, to establishing a result about the theory Q,
which was what I called the sigma 1 completeness, that if you have a sigma 1 sentence, existential quantifiers and then bounded quantifiers, and it's true, then it's provable in Q. We've proved a lemma A that says you can compute the values of the arithmetic operations, a lemma B that says that less than equals of when you're bounding it by a fixed number, by a numeral, can be reduced to can be expressed as a finite disjunction. So these are the main lemmas really, and I mean we now have another lemma, but it's basically most of the result itself, and this is that Q is going to be, we want to prove it's sigma 1 complete, but we're first going to prove it's delta 0 complete, and that's most of the work in proving that it's sigma 1 complete. So let's call it lemma C. I need to find it in my notes. Had a whole break to be on the right page of my notes, and I failed to do that. Let's check. Right. So this says if we've got a delta 0 formula, and actually we'll, in order to make the proof of the lemma go through, we won't just consider a sentence, we'll consider a formula with some pre-variables. So this is a delta 0 formula, so only involving bounded quantification. Then, well, we'll turn it into a sentence by instantiating the free variables with numerals. So for all numbers in the real world, n1 to nk in a set of natural numbers, if the formula A with the numbers n1 to nk, their numerals, instantiated for the variables is true in the real world, then Q proves that formula. So in other words, Q is delta 0 complete. So we want to prove this, and again, it's going to be another proof that, so this is a family of statements where we're now saying, so we're stating that collection of formulas are provable in Q, and the collection of formulas is given by, we consider only those delta formulas that are delta 0 with their variables instantiated by numerals by some given family of numerals. So to prove that, we're going to prove this by induction on what we call induction on the structure of the formula A, or if you like, on the size of the formula A. We're going to break the formula A down into, A is a formula built up using the propositional connectives and bounded quantifiers. And in each case, we show that if we've got a complex formula, say one, it's a combination of two connectives, as long as this property holds for the subformulas, then it applies for the outside, the whole formula itself. So I call this induction on the structure of the formula A. We're going to consider one case for each possibility of the formula A. So formula A could be built using, as its outermost connective, a propositional connective, or it could be built using, with its outermost constructor, a quantifier, which must be a bounded quantifier, so either a bounded universal quantifier or a bounded existential quantifier. I'm just going to consider one case, which is
case in which A is a bounded universal quantifier, so A is of the form for all x less than or equal to t, B. So in this case, B might have x as a free variable, and it might have some other free variables, x1 through to xk. So suppose B has free variables x1 through to xk together with x, and the induction hypothesis, let's put it in blue again, is that the property we're trying to prove holds for the formula B. So the induction hypothesis that we have to work with is that so for all n1, nk, and n, if the formula B instantiated with the numerals for n1 up to nk and n is true in the natural numbers, then I wish I'd taken up a bit less space, but anyway, let's take up less space now. And it's provable in the, well, it's the same instantiation there. But n1 through to nk and n, that's the same instantiation of the three variables. The formula B is provable in. See, I don't want to put that in a box.
You have the numerals here when it's in natural numbers, or is it just that? And
We have. We're going to put. We don't need to, but I'm turning it into a formula, so I'm instantiating these terms. I'm substituting these terms. But I could also use the notation without the numerals, and then that would be an environment interpreting the variables, yeah, or parameters interpreting the variables. It's the same thing because, of course. Oh my goodness, I've just drawn on my shirt. I don't quite know what's wrong this morning. I poured my drink over my shirt during the break as well. So, I wonder if the eraser works. I don't think that's going to. Oh, I probably won't wear this shirt again. We shall see. Anyway, where are we? So we've got the induction hypothesis, and what we want to prove in this case is we want to prove that if for all x less than or equal to t, B with the variables x1 to xk instantiated by the numerals n1 to nk, if that's true in the natural numbers, then and it's true, then it's provable in Q. So suppose that for all x less than or equal to t, the with n1 nk instantiated for the three variables is true in the natural numbers, and we need to show this right-hand thing. So we've got a term t that might have some free variables from x1 through to xk in it. If we instantiate those free variables with numbers, with the numbers n1 through to nk, we'll get an actual number m. So let let m in the natural numbers be the interpretation of t with now interpretation of the term t with now with the numbers n1 to nk interpreting the three variables, which is the same thing as if I was substituting the numerals there. It doesn't really matter. So in the natural numbers, this bounded quantification is true, where t is with this instantiation of the three variables is given the value m. So for all x is less than or equal to t is the same thing as saying, well, b is, sorry, I don't know. Yeah, that's right. This is the same thing. So then, if this bounded quantification is true, then in the natural numbers, we certainly have that b n1 through to nk is 0 is true, and because we know what universal quantification means, and the bounded universal quantification means in the natural numbers. So if we count the variable x up from 0 to m, the conjunction of all those formulas is true. It holds, b holds for 0, it holds for all x less than or equal to t, so it holds for 0 for x, for 1 for x, all the way up to m for x. So by the induction hypothesis, which is by the induction hypothesis, where we've got a for all over n here, so we can change the variable n we're applying it to. So we've got n implies, so each of these conjuncts is true in the natural numbers. So by the induction hypothesis, each of them is true, is provable in Q. Sorry, the induction hypothesis here, each of them is provable in Q. So by the induction hypothesis, that conjunction is itself provable in Q. So Q proves the with n1 to nk instantiating x1 to xk in 0, and all the way up to n. So equivalently, because it's a logically equivalent formula, Q proves that if the disjunction for all x, we can make a finite disjunction here. If x equals 0, or x equals 1, or all the way up to x equals n, then the n1 through to nk with x, okay? And if you can prove a conjunct with, you've just got these different instances for the variable x, then you can put them all into a disjunction here, and if any one of these is true, then this is true. That's simple logical reasoning. So by our lemma A, not B, not A, B, by our lemma B, the right to left implication, we've got this, oh. Well, anyway, one of the implications, well, it's equivalent. So by the lemma B, so by lemma B, this disjunction can be replaced with so for all x, x is less than or equal to m. That's the same as that disjunction implies b n1 to nk x. So here we're using the left to right implication of lemma A, and that was indeed the one that required the
the more intensive proof, fortunately. So that, I mean, that was the difficult part of lemma A. Sorry, not lemma A, lemma B. Okay, so we're almost there. There's one little thing to do. We want to replace this with T. That's by our lemma A. By lemma A. So our term T is a term, so it involves successor, plus, and multiplication, probably some sort of complicated combination of them. We're instantiating all the variables with numerals. Lemma A allows us to compute out the numerals down to the resulting number. So by lemma A in Q, we have that T with the variables instantiated by the numbers n1 to nk that we used to get the value m, that this equals that equals the numeral m. So we can replace this m here with t. So indeed, this is what we wanted to prove. If we replace this with t with n1 to nk instantiated, what we indeed have is that for all x is less than equal to t. For all x is less than equal to t implies b, with the x1 to xn instantiated with n1 through to nk. There we go. Is provable in Q as required for that case. So then, this together with the existential quantifier are the most. Maybe the existential quantifier is easier actually. Anyway, this is the most complicated case of the whole proof. You can, if you want, check some of the other cases, but I think we'll take that as the end of the proof of lemma C. And having done that, having proved lemma C, we can now finally, goodness me, it's a lot of work to do something very basic in a sense. And the other thing about this is there are no interesting ideas in the proofs. We're sort of just basically churning along using the axioms. It's good to see that it can be done. The interesting ideas are essentially in the choice of the axioms of Q itself. So somehow the formulation of the theory Q is justified. I realize I didn't change the camera as well. So the formulation of the theory Q is basically motivated by getting these results to work out. So now we can finally prove sigma 1 completeness. And then having done that, we can get to proving our main result. So proof of sigma 1 completeness, and this is now easy. We're just going to do it directly, hopefully. Let's look at the notes. Yeah, so suppose suppose the sigma 1 sentence is true in the natural numbers. So for this to be a sigma 1 sentence, A needs to be a delta 0 formula. We've got the delta 0 formula preceded by some existential quantifications. So where A is delta 0. The point is, this is a sentence. So there are no other free variables in A. Sentence. So we're saying this formula is true in the natural numbers. Well, what does that mean? Well, it means there actually exist natural numbers in the real world, n1 up to n sub. Make that, well, was I using n? I was using k before, let's make it k. There exist natural numbers n1 up to nk making A true. That's what the existential formula means in the real world. So there exists n1 to nk such that
A is true for, let's write them as parameters, but that's the same thing as, so here I'm interpreting the variables as the values n1 through to nk in the structure. That's the same thing as substituting the numerals in well, the variables x1 to xk, because the numerals represent their numbers. So by delta zero completeness, which was lemma C, Q proves that A is true with n1 up to nk instantiated. So if we can actually prove that A holds for some particular terms, then of course we can prove that there exist values such that that's just the rules for existential quantification. So indeed, we can prove the original formula. And we're done. And that you'll be pleased to hear, well, I'm certainly pleased to be able to say it, is the end of our manipulations with the theory Q. We're not going to do well, it's the end of my manipulations with the theory Q. You've got an exercise class tomorrow. I don't know. You might get to enjoy it. So you never know. Right. So where are we? Well, we want to prove a theorem that any computably axiomatized one consistent extension of Q is incomplete. We have that. Let's erase the word. We have that Q is sigma 1 complete. Of course, any extension of Q is also going to be sigma 1 complete, because being sigma 1 complete says if we have a true sigma 1 sentence, we can prove it in the theory. We have an extension of Q, we can only prove more in the theory. So to summarize where we are. So Q is sigma 1 complete. Hence, any extension of Q is also sigma 1 complete. So our main result is any consistent, computably axiomatized extension of Q is incomplete. What we're going to prove, and now we're going to get, we shall prove something that implies that. So, theorem, so if T is a consistent, computably axiomatized so I'm going to strengthen that to one consistent again, extension of Q, then T is undecidable. In other words, we don't have, I mean, we've done this many times, but we don't have an algorithm that, given a sentence, will say, is it provable in T or not? This is the same as the theorem I stated before, except that I've replaced incomplete with undecidable. But you might remember from 2 lectures ago, the lecture on decidability via model theory, we had a result that connected completeness and decidability. So incompleteness then follows from, well, that lecture is called Janicak's theorem, which I shall just remind you of, which was if T is computably axiomatized, and complete, then T is decidable. So we had this 2 lectures ago, so I won't talk you through it again. So actually, rather than proving incompleteness, we're going to prove undecidability. And this is the point at which we're going to borrow some results from computability theory. For those of you who've done computability theory, this will be straightforward. For those of you who've not done computability theory, try to understand at a high level what I'm saying. It doesn't matter if you don't follow all the details, because in 2 weeks' time, we're going to do Gödel's own approach to proving incompleteness, which is going to be self-contained anyway. So the results from computability theory now is just to get the point of it is to get a quick result establishing the incompleteness. So last week, I proved that it's almost like a Dalmatian dog. It's hard to get the spots off. And these 2 spots are permanent. Anyway, yeah, so last week we proved that the exponentiation function is sigma 1 representable. So its graph is represented by sigma 1 representable. In fact, there's a generalization of this, which I already mentioned last week, but you can now understand better after last week's exercise class, which is that every primitive recursive function is sigma 1 representable. So you did the primitive recursive functions in the exercise part last week. And the proof of this is not really any more difficult than the proof of the exponentiation function. You again use a sequence of approximations to approximate, or the sequence of the things you compute by iteration to get to the value of a primitive recursive function. I'm not going to prove this in the lectures because it's basically the same proof again. It's just a lot more fiddly because you have to deal with all the notation of primitive recursive functions at the same time. So kind of the proof of the exponentiation contains the main difficulties, and a very straightforward but nasty to write down generalization of it proves this, that every primitive recursive function is sigma 1. It's not that nasty to write down, but it's nasty to explain. Representable. And then the proposition from computability theory which is, and I've also again forgotten to move the camera. The proposition from computability theory is that there exists a primitive recursive binary function t xy such that the set of natural numbers n such that there exists an n such that t m n equals 0 is undecidable. So you can encode such, for those who did computability theory, you can encode such a thing very easily using Klee's t function. Another way of thinking about it is that this could be the set of codes n for elements of Klee's halting set, and m is, and we can say that t m of n equals 0 if n is the number of, if n halts on its own input, and m is the number of steps needed to compute to the time that it halts. Anyway, it doesn't matter. For our purposes, all we're going to need is this result, which those of you who did computability theory will think about it. The rest of you can just accept it. And given this, we have the proof of our undecidability theorem, from which our incompleteness theorem follows. So our undecidability theorem, that if T is a one consistent computably axiomatized extension of Q, then T is undecidable. So I'm going to prove that, and then that's the end of today. And next time, we'll have the work on the axiomatizations behind us. We won't need to do more fiddly proving things in the theory queue. And next time we'll go through the rather wonderful vision of Gödel for how he saw these incompleteness phenomena arising. Did not use computability theory, but rather the ability of the language of arithmetic to formulate sentences that are self-referential, that they can express properties of themselves, which is a rather curious and very interesting phenomenon. So anyway, for our quick result today, once we've gone through the painful process of proving things in Q, we can now get that from the ingredients we have. So proof of the undecidability theorem, by which I mean this one in the red box here on the board. So proof of undecidability theorem. So let T be a one consistent, computably axiomatized extension of Q. Yeah. So suppose for contradiction that it's decidable. Is decidable. We can now, the point is we can now decide membership of this set here, this undecidable set that this proposition says. We now decide membership of set of numbers n such that exists T and N equals 0 by the following algorithm. The point is, given a natural number, we want to decide if that natural number in this set. The algorithm is input n, and now ask the question, is it true that the theory T proves exists to Y G sub T of the numeral for encoding n, y, 0, where G sub T is the sigma 1 formula, representing T, this function that we have in this proposition here, this function little t from the proposition. We've got little t, which is the primitive recursive function we're using to define an undecidable set, and the capital T, which is the theory capital T. And the point is, this existential quantification, this is going to be true. This is exactly saying there exists an M such that little t applied to n equals 0. That's exactly what this is saying. So this will be true if and only if the number n is in T. Is in this set. So this is true. The above thing is in black. This is true if and only if n belongs to the set. Okay. Exists in n, T and n. 0. So is this true? If so, return yes. Otherwise, return no. And we're done, but there are a couple of things to explain. So where did we use the computably what? Well, where did we use one consistency? That we used one consistency because here we have a sigma 1 sentence. The point is, this is provable in T if and only if this is true in the real world. So if and only if this number is in here. So this, if and only if this is by one consistency. In one direction, so this implication, and by sigma 1 completeness. So the right to left implication here is one consistency, and the left to right implication is sigma 1 completeness. And I was going to say, when do we use computably axiomatized? And actually we don't. So the main statement of the theorem, I only just realized this, the statement of this theorem, we can remove computably axiomatized. Because if it's not computably axiomatized, then it's in any case undecidable. Any decidable theory is by necessity computably axiomatized. So, because the theory itself is its own, if it's decidable, the theory itself is its own computable axiomatization. We also had that 2 lectures ago. So the main theorem here that we're proving is if T is a one consistent extension of Q, then T is undecidable. So in particular, as a consequence of this, the true theory of the natural numbers is also undecidable, which wasn't a consequence as I'd formulated it before. Okay, so that's everything for today. Let me pause the recording.